issues I have to talk about. So every semester, I will get an email from the provost telling me about the various holidays from different cultures, reminding me that on these holidays, I should try to make accommodations for the students who want to celebrate those their own holidays. Anyway, so there are many of them. Okay, so it turns out today is a big Chinese holiday. Okay, I know that because of course I'm Chinese. So I know that also there are other sort of ethnicities that will celebrate this holiday. So this is what I decided to do for all of you who want to celebrate your own holidays, okay, not just Chinese holidays. So you're welcome to leave, and I'll be happy to give you my notes, and also I'll be happy to go over the notes with you at a later time. Okay? So of course, that's because today is a Chinese holiday, so all of you who celebrate this holiday, even though you're not Chinese, you're welcome to leave. Okay? So I'll give you my notes, and I'll go over the notes with you later. Okay? If you want to. Okay? All right? So now is the time to leave if you want to. No? Okay, so anyway, okay? Anybody who wants to celebrate this holiday can leave too. No? I guess I cannot escape today's lecture. So I was hoping all of you would leave. And then I get to celebrate too. So, well, anyway, so if not, I guess we'll carry on. Okay, so there are a few other things I will mention. All right, so first, the help session for from my assistants. Okay, the location has been changed to 318 upstairs. Okay, so the previous room was too small. 318, that's the new location. Okay, so time is the same. Tomorrow, I think it's from 5 to 6. Okay, right? 4 to 5. Thank you. Okay, so that's that. I've also updated the file. That has this information on Canvas. Okay, so there everything is updated. All right, so to help you visualize the cylindrical volumetric element and the spherical volumetric element, okay, so I made two figures using MATLAB, okay, to help you visualize those things. And so for some reason it's very slow. that's the phi, sorry. Here we go. Okay, so you can see that x direction, y direction, and z direction. Okay, so cylindrical focus system, r direction would be inside every xy plane going that way, and theta going that way. So you can see here, and this would be the dr. Okay. And this would be the r d theta, so that's d theta, okay? And this would be the dz, okay? And also you can rotate this, of course, to help you look at different, look at this from a different angle. So to this, this surface, see, this is the normal direction, surface with the normal direction in the theta direction, right? So this is the surface in the r direction, and that's the z direction. Okay. Anyway, so this is the cylindrical, and there are also the spherical. Okay, so the spherical x, y, and z. So here the r direction is from the origin to any direction, right? So this would be the dr. Okay, so then theta direction. Theta angle is the angle formed by z and r, so that would be the theta. So that means, so this is dr, and this is the r d theta, or this angle here is d theta, okay? And phi is the angle formed by the projection of the r vector and the x axis, so that's that angle. So that means this is because of d theta. So the r sine theta d theta is this element, okay? So again, we can also rotate this to look at different surfaces. Okay, all right? So, of course, then here, and you'll be able to see that this surface right here is going with the phi direction of the normal direction, okay? This r direction, and this would be the theta, okay? It's theta. So this is the normal direction in the theta direction, okay? The normal direction of the surface. So I put this on Canvas, so of course you can download and play with it if you have a hard time of visualizing the different surfaces in volumetric elements in these two sort of coordinate systems, cylindrical and spherical. Okay? So that's that. There's something else. Yeah, so. I put two new handouts on Canvas. So this is handout number 3. They're basically some constants and conversion factors. Hopefully that will be helpful for you when you look at the notes or homework solutions and other things. Okay, so handout number 4 we're going to use later. So turn this off. All right, so we're done with the shell dynamics method. Okay, so, and we used that method to talk about 3 examples, and we practiced some too, right? So, and today we're going to start a new topic. Okay, so far, all our discussions were sort of centered around one type of fluid. So that is the Newtonian fluid, where the stress, shear stress, and the velocity gradient have a linear relationship. Okay, so we have a constant viscosity. Okay, so today we're gonna start to talk about non-Newtonian fluids. And of course, once we talk about a few different non-Newtonian fluids, we're going to look at how we can use the shell balance method to solve the flow of non-Newtonian fluids. Now that's, of course, because in biomedical engineering, it's rare to sort of encounter Newtonian fluids, okay, in humans. Plasma is Newtonian, air, there it's compressible, it's a little more complicated, okay, so, yeah, anyway, so very rarely you're going to see Newtonian fluids in humans. So that's fine, okay. So. All right, so let me go back to one of the equations we've derived in the last lecture, or maybe this one. Let me see. Yep, so this is one. So this is the volumetric flow rate we've derived for a tube flow, okay? So Q is equal to this. Now this is actually a formula that was used by Hagen and Pazuye when they studied the flow of a Newtonian fluid through a circular tube, okay? So basically, you know, they apply different pressures and they use tubes with different lengths and radii, okay? And study how much is flowing through, okay? So then, of course, we know this equation, okay? Now, you can see here, using this equation, if you have a circular tube, what you can also do is to measure what? Viscosity, okay? Say you have a fluid, you don't know what viscosity is, okay? You let this fluid flow through a circular tube with known length and radius, okay? You collect the fluid, so then you will know Q and pi, you know the pressure, of course, then you can calculate this viscosity, okay? So that's one way to calculate or to measure the viscosity of a fluid, okay? So if you do it like that, so that kind of device is called a viscometer, or more specifically, it's called a capillary viscometer, okay? Because the radius of the tube is tend to be very small, okay? All right, so viscosity can be measured with the Pazuye flow, and if you do this, and then you use tubes with small diameters, of course, to save the sample, okay? So that's called a capillary viscometer, okay? And of course, you may have heard other viscometers too. Basically, there are quite a few other devices we can use to measure the viscosity. Now, one of them is, well, viscosity can be also measured with other viscometers like the cone plate viscometer. And the advantage of this viscometer is that the shear rate in this viscometer is uniform, or is so you know that in the capillary viscometer there, in the tube flow, the shear rate basically it's that velocity gradient, dV/dr, is not a constant, right? So it goes from 0 at center to largest on wall. However, if you use the cone plate viscometer, so basically you have a cone. We have a very small angle, okay? And then you use a flat plate at the bottom. So you can show that in that kind of viscometer, the shear rate at different locations, they are more or less the same, okay? So that's the advantage there, okay? There are other viscometers I'll mention when we get to them, okay? So using the cone plate viscometer, and we can do experiments like this. You can apply different shear rates. Let's call it gamma. And then measure the shear stress of a certain fluid, okay? Say we put plasma in a cone plate viscometer. You apply different shear rates, okay? And then you measure different stresses. And you'll find out it will behave something like this, okay? Because we know plasma is a Newtonian fluid. You increase the shear rate, and the shear stress will increase linearly with the shear rate, okay? So of course, the slope here is the viscosity, right? Okay, so I'll call this line number 1, okay? So number 1 is what we call the Newtonian fluid, okay? So, for example, now we want to know blood, okay? What kind of fluid is that? Is it a Newtonian fluid? Okay, you put blood here, and you apply different shear rates, okay? So then you'll get some different stresses, you plot them, and then you'll know whether it's Newtonian or not, right? So, and we'll see what type of fluid it is of blood later, okay? So for now, let's discuss other different kinds of behaviors. Now, there's a certain fluid, okay? You put it in the viscometer, you apply shear rate, so basically you try to rotate, apply shear rate, right? You'll find out that, well, if the force or torque you apply is not big enough, there'll be no movement of the fluid that's inside the viscometer, okay? So you have that torque you apply has to be large enough for the flow to occur. So that means, well, the shear stress has to be large enough, right? So then, after that, you measure shear stress again, you get another linear relationship, okay? The difference is what? Here, okay? Before the stress reaches a high enough level, there will be no flow, or no shear, sorry. That's a better way of saying it. Before the stress reaches a certain level, there will be no shear, okay? After that, there's shear, and then shear stress again will have a linear relationship with the shear, okay? So this is the second type of fluid, or second type of behavior we're going to discuss. This is called a Bingham plastic. So in this case, there's a stress value you need to overcome before you see any kind of shear of the fluid. So that's this yield stress. We call it tau sub y, okay? So this value here is the yield stress, okay? All right, so the second kind of behavior. The third one is something like this, okay? You apply different shear rates, you measure the stress. Well, the stress will not have a linear relationship with the shear rate. Instead, you get something like this. So basically, the shear stress will be larger and larger and larger, okay, compared with a linear relationship, okay? So this is the third type. So definitely there's shear here, okay? It's just that shear works a little different. So I mentioned before that for this line, the slope is the viscosity, right? The viscosity is a constant. Now, if you look at the slope here, it's not a constant. The slope is getting larger or smaller? Smaller, right? Okay. So if we still interpret the slope as the viscosity, that means what? The viscosity is getting smaller and smaller, right? So in other words, the viscosity getting smaller and smaller means, remember what the viscosity represents, right? It represents molecular interactions, but also how resistant a fluid is to the flow, right? So if the viscosity getting smaller and smaller, that means the resistance to the flow is smaller and smaller. That means the flow should be easier and easier, right? Okay, so that's why this third kind of fluid is called a shear thinning fluid. It's like, right? You're using a fluid that has a smaller and smaller viscosity. It's like it's getting thinner, the fluid, right? So we know generally, if a fluid has a higher viscosity like honey, it's thicker, right? So it's getting thinner, and then that's shear thinning, viscosity getting smaller, okay? It's also called a pseudoplastic fluid, okay? Pseudoplastic or shear thinning mean the same thing. The fourth one we're going to discuss is the other way, the other behavior. So the shear stress will also increase with shear rate, but it curves a different way. It curves like this. So this is number 4. So number 4, of course, you can see the slope is getting larger and larger. So the viscosity is getting larger and larger. So you know what this is called, right? So instead of thinning, it's called shear thickening fluid. Okay? It's also called a dilatant fluid. Okay? All right, so these are 4 different non-Newtonian fluids. Okay? So not 4, sorry, 3. One is Newtonian. So we're going to discuss Kingham plastic first. Since that's the easiest of the 3, it's linear, right? So we know when the stress is less than the yield stress, this kind of fluid has no shear. We should not say no flow, okay? And later you'll know why. But for now, let me tell you, no shear is correct because although the fluid itself, no shear means there's no relative movement of the molecules or particles inside the fluid, okay? But it does not mean the fluid itself cannot move as a whole, okay? Later you'll see an example where the fluid is moving, but shear rate is 0, okay? But it's moving, it's flowing, okay? Shear stress is less than the yield stress. It's flowing, but no shear rate is 0. Okay, you see that example later. When the shear stress is larger than the yield stress, of course, the relationship between the shear stress and the shear rate, that's easy, right? Easy to come up with. So before you have tau equals to mu times shear rate. And now it's simply yield stress plus mu and shear rate, right? So the yield stress is like the intercept, right? So, okay, so for a simple equation here, some examples. This one's kind of easy to find examples. So mayonnaise, toothpaste, mustard, chocolate. Of course, it's not the solid chocolate, okay? It's the one that's melted, okay? So it flows like a Bingham plastic, okay? So then we'll discuss the power law of fluids, okay? You may wonder, well, we never mentioned this, okay? We only mentioned shear thinning and shear thickening. Well, it turns out for both behaviors, you know, this can be represented by power functions, right? Okay? It's just that the power will be different, okay? So, power law of fluids. Well, it basically means that the shear stress and the shear rate have a power law relationship like this with two parameters, m and n, okay? All right? So the m and the n here, that's what we call the material constants, which means if you wanted to describe a certain fluid using the power law equation, like this one, m and n should not change once that fluid is determined, okay, is defined, okay? If it changes for the same material, then you cannot call it constant. Then you cannot use this equation, okay? All right? So m and n should be constants for once the fluid is determined, okay? Of course, you know that there's a special case. When n is equal to 1, this is simply what? Newtonian. Because in that case, of course, it represents a linear relationship, and m will simply become viscosity, right? Yeah.
I'm sorry, could you spell from that? I didn't find the last one.
Okay. All right. So now, how can we use this equation to describe the shear thinning fluid? Okay, so there, it's shear thinning. The slope is getting smaller and smaller. Do you think we should use a n number larger than 1 or less than 1? So remember those different curves, okay? Like x squared, you know, or x to 0.5, okay? So n is larger than 1, you get a slope, right? You do the slope, and you will know that that slope will be smaller and smaller, okay? So the reason, of course, is simple. You just need to differentiate this ones, right? So you have gamma n minus 1, right? So then you have m and n. That's your slope, right? So, and then you know that one will increase sort of slower than the linear function, right? So Okay? Examples here. So it turns out this equation is fairly useful for biomedical engineers because very often you will use what? Polymers. The high molecular weight polymers, if you make a solution, high molecular weight, polymer. Okay, so then a lot of these can be considered shear thinning fluids. Now, why it's shear thinning for high molecular weight polymers? This is similar to blood, which, yeah.
If the exponent is greater than 1, would the slope be increasing? Or would that be shear thinning?
Let's see. So the slope is m and gamma n minus 1. N is larger than 1. So this is larger than 0, larger and larger. You're right. So, sorry. Thank you. I don't know what I was talking. Yeah. Okay, thank you. Okay, so this is where I'll give you this new handout. So this is table 8.31 from that recommended textbook. So these are a few examples of sort of solutions of high molecular weight polymers. Okay, so you see the different kinds. So the different temperature means these are the parameters that were measured when these solutions are at different temperatures. Of course, you know that temperature is a major sort of factor that can influence the viscosity value. Okay, so different temperatures, different parameters for m and n. Okay, so you can see here all these n's, they are less than 1. Okay, shear thinning. Now the reason for the shear thinning is that at low shear rates, these polymers, they tend to form aggregates. Okay, they tend to, adhere to each other. Okay, now when you increase the shear rate, okay, the larger shear rate will break these molecules up. Okay, so the aggregates will be smaller and smaller. Eventually, they all break up. So that will decrease the viscosity. Okay, all right. So that's why. All right. So this is on canvas. This handout. Other examples. Ketchup. Paint, most of them. Whipped cream. And here's one example that will be of particular interest to all of you. The synovial fluid that's in the joints, in the knee, okay? And this is interesting, okay? So you can see that the synovial fluid, it's shear thinning, which means what? When I'm walking, okay, and I have to bend my knee, right? So you're actually applying shear to the synovial fluid there, okay? So this shear will make it thinner. In other words, the viscosity will be smaller, okay? So that'll make the movement easier, right? Okay? You can imagine that if it's shear thinning, it will make the movement more difficult, okay? So That was something that's interesting. And actually, of course, this was found by environmental engineers. Okay, so. So when n is larger than 1, that's shear thickening. All right, so we don't have a lot of examples here. This shear thickening usually occurs in suspensions. So I'll give you two examples here. If you ever cook using starch, you know the mixture of cornstarch and water is something like this. Okay, so basically you stir it a little more. Okay, it will get thicker. Okay, the viscosity will increase. Okay, and the other example is the wet sand. So if you ever walked on a wet sand beach, okay, so you'll find out you won't sink, right? So that's all. That's because that's the wet sand is shear thickening. When you step on it, the resistance will get larger and larger to shear the sand and the water mixture. Okay, so all right, so okay, so 4 different kinds. Okay, Newtonian being plastic, shear thinning, power law and less than 1, shear thickening, power law and larger than 1. So different relationships between the shear stress and shear rate. Okay, so before we talk about blood flow, blood is non-Newtonian, and none of these equations can be used for describing the blood flow or the blood as a non-Newtonian fluid. So first, before we talk about those, let's talk about how a power law fluid will flow in the tube. Since we talked about tube flow was our last one of the topics we covered, right? So one of the examples we discussed. So basically everything is the same there, except that the Newtonian fluid will be changed to a power law fluid, okay? So if we look at a flow like this, how we can look at basically all the momentum transport questions we've looked at before, okay? So I guess the first question is, can we still use the shell balance method to look at the momentum transport here? Of course, right? Because the shell balance method is what? Simply says, well, the change in the momentum in the control volume is equal to E minus out plus generation minus consumption, right? It never sort of specifies what type of fluid flow it is, right? Okay, so that can be used for any kind of fluid flow, okay? So that is out of the way. So that means we can still use the shell balance method to solve this problem. Let's go back to the tube flow. All right, I have to see that diagram right here. All right, so this is the pressure-driven flow. So I mentioned everything else is the same. The only thing that's different is the type of fluid that's in it. Okay, so it's a pressure-driven power law fluid flow. Okay, everything else is the same. You look at what we went through. Okay, pressure-driven, pressure, long tube, fluid developed, and everything. Okay, everything. Okay, so I mentioned that you can still use what? The shell balance method. Okay, so this is the shell balance method. Okay, so in everything we've discussed here, did we use the fact that in this case here, the flow is a Newtonian fluid flow? Did we use that fact in these discussions here? Not the one afterwards, here, when we used the shell balance method. We didn't, right? We didn't, although we did consider the Newtonian fluid flow here, but when we used the shell balance method, we never used the fact that the flow is the Newtonian flow, right? Because we didn't have to, okay? So that means what? All the discussion here about the shell balance method can be used for the non-Newtonian flow, okay? Because you look at the moment going in, same as whatever type of fluid flow it is, doesn't matter. This is still the same, okay? Right? And later, when we look at the stresses, forces on this volumetric flow fluid element, did we use the fact the flow is the Newtonian flow or the fluid is a Newtonian fluid? No. See, it's all about the stresses, okay? You can calculate stresses using Newton's law, but if the flow is non-Newtonian, you can still have stresses, right? It's just that the equation you use to calculate stress is different, okay? The force is still there. Force divided by area, that's still the shear stress, okay? Stress never mentioned what type of fluid it is, okay? All right? All the way until here, okay? And all the way until here. And all the way to here. So from this here above, we never cared what type of fluid it was, okay? So that means it's okay to use everything here for non-Newtonian fluid, okay? And of course, once you get to this part, it's different, okay? Well, you have to use the relationship between stress and velocity, and then this is Newtonian, okay? All right? All right. This means what? All these equations here we've derived can be used for this new flow we're trying to look at. This one, okay? I don't know what you should write there about everything I've said. I guess if you write one sentence, it should be all the stress equation we've derived in the tube flow can be applied here because, you know, we never cared what type of fluid flow it was before when we derived that equation. And that equation is right here. So this is what I copied from there, okay? When we derived this equation, we never used the fact that the fluid was Newtonian, right here, the equation, okay? Right. There is another reason why we can use this equation for a non-Newtonian fluid flow. The reason is what? This equation basically represents the mechanical force equilibrium of a volumetric flow element, fluid element, okay? For example, if you consider the mechanical equilibrium of this, you get that equation too. So that means, since this equation is about mechanical force equilibrium, so that means whatever type of fluid flow it is, doesn't matter because it represents what? Force balance, okay? So that's another reason why we can use this equation here. And we didn't do force balance, but if you're interested, you can try to do it yourself, or I can show it to you in my office, okay? So, anyway, all these discussions, okay? I was trying to use these discussions to basically let you know that this equation can be used here, okay? We won't have to go through those steps anymore, okay? All right? So, of course, once you want to try to relate the stress and the velocity together, that's where it's different. So we know for a power law fluid, stress should be related to shear rate with this equation, m times shear rate to the nth power, okay? So what's the shear rate in a tube flow? The shear rate shear rate in this case is, where is it? Right here. It's here. Right? dvzdr. It's basically the velocity gradient, right, in the r direction. That's the shear rate. Okay. So, in the tube flow of a power law fluid, is the shear rate the same? How would you calculate shear rate in that case? It's still the cylindrical Carnot system, right? It's a tube flow, so the same cylindrical Carnot system, the same vz, right? You have a velocity in the z direction. How that velocity is changing, or in which direction the velocity is changing? R direction again, right? So how would you calculate the velocity gradient? Of course, you do dvzdr again, right? That means the shear rate is the same, okay? All right? However, is dvzdr larger than 0 or less than 0? Less than 0, right? Because, see, when r is increasing, the velocity is decreasing. Remember, velocity is the largest at the center, right? Okay? Smallest on the wall when the radius is the largest, okay? So dvzdr is less than 0. So that means if I tell you gamma only represents the magnitude of the shear rate, okay? So this shear rate here, if I tell you this gamma is the shear rate of the magnitude only. So for a tube flow, what is gamma equal to? Is it equal to dvzdr or negative dvzdr? We know this should be gamma, right? And we know it should be dvzdr, or either positive or negative. If gamma is the magnitude only, so it should be equal to positive or negative dvzdr? Negative, right? Because, see, dvzdr is less than 0. If you want to use the magnitude, you add a negative sign so that it becomes a positive number, okay? All right? So now you can see how we can get velocity, right? The stress, which is equal to this, and you have dvzdr here. So this is what? An ODE, right? Okay? So from here we can solve this. So first we can get the shear rate, which should be 2ml r to the power of 1 over n, right? So divide both sides by m, and then you do the power of 1 over n on both sides. And then the right-hand side will become this, the left-hand side will become this, right? Okay? So of course, you know how to solve this, right? It's a very simple ODE to solve. All you need to do is to integrate. You multiply both sides by dr, and then integrate from 0 to r, okay? So for the velocity, so put the negative on the other side. Negative P0 PL 2mL 1 over n and n plus 1 r to the power of n plus 1 over n plus a constant, right? So you integrate, there should be an integration constant, okay? All right? So when you integrate r to the power of 1 over n, you get this, right? Okay. And this is that constant we need to determine from the boundary conditions. Of course, the boundary conditions here are the same as what we've used before on the wall, as long as we think there's enough adhesion between the fluid and the wall, we can assume the no-slip boundary condition, okay? And of course, if you have a non-sticky fluid, and then this is different, okay? So there are other boundary conditions we can use. All right? Only one constant, so you can plug in and determine the constant. And you'll find out the constant is this much. So now I can put the constant back in and get the solution for the velocity. And factor some constants out. You can arrive at this expression for the velocity. Okay? All right, so the velocity, again, is the smallest on the wall, right? Equal to 0. So where is the largest? Just like before, right? At the center, when r equals 0, it should be the largest, because everything here is a constant. It should decrease when r increases, okay? So that's where it's the largest, okay? What else? Average velocity, okay? Can you calculate the average velocity? Of course, just like before, okay? Vz, dv, 2 pi r dr, right? 0 to r, integration. What else? Mass flow rate, that's easy. The force, right? So the shear stress. So once you know V sub z, of course, you plug that V sub z back here, you can get the shear stress at any location, right? So once you can calculate the shear stress at any location, of course, you can also calculate the shear stress on the wall shear stress, right? So once you know the shear stress on the wall, you can also calculate the force applied by the fluid to the wall or the other way around, okay? Everything we've done in the Newtonian tube flow, okay? All right? So these are all the things you can do. So force, flow rate, average velocity, maximum velocity, and W, the mass flow rate and everything, okay? All right? So we won't do that because, the formula is the same. It's just math, okay? Again, everything, every time I skip some steps, it's a good opportunity for you to practice, okay? Of course, we know if you practice, how would you know your answers are correct? This is a special case you can use to check your answers. N equals 1, M equals mu. For this case, it's what? It's the Newtonian fluid flow in a circular tube, right? Okay? So you get these numbers, you let N equals 1, M equals mu. You should have the same expression as we got from the Hagen-Pasuya flow. So you can use the results there to check your answers, okay? If you do practice. All right, so far, what we've done. Introducing you to a few non-Newtonian fluids that are simple enough, where we have simple equations or relationships between stress and shear rate, okay? And then we looked at one example, the parallel fluid flow through a circular tube, okay? So now, if I ask you to look at a Bingham plastic fluid flow through a circular tube, do you know how to do it? Kind of, right? Okay. So I mentioned that as long as there is flow, this equation is always there. The difference is what? There's yield stress in the Bingham plastic flow. Okay, that's where it's different. Okay, so for that, let's talk about blood. Because once you know how to deal with blood flow in a circular tube, you know how to deal with the flow of a Bingham plastic in a tube flow. To talk about blood flow, we'll first need to talk about blood rheology. Well, rheology simply means the study of deformation and flow, especially of non-Newtonian fluids. Okay, it's like fluid mechanics. Okay, so. What's in blood? I'm sure you all know there's plasma. Plasma basically is a dilute solution of stuff. Salts, sugars, proteins, ions, and things, right? Okay? What else? Cells. Erythrocytes or red blood cells. Leukocytes or white blood cells. And platelets. Some people would not call platelets cells, but that's okay. I mean, we're not trying to study biology here, but so these are the major components, right? Okay. So I mentioned before plasma. Well, you can consider that as a Newtonian fluid, okay? But blood is not a Newtonian fluid. One of the things that will affect how blood behaves when it flows is this parameter called hematocrit. Okay? If you ever seen some tests that they do in hospitals, this is a common sort of parameter that they look at. Hematocrit basically is the volumetric ratio of red blood cells in blood, okay? Volumetric fraction. For men, this number is, on average, is 47%, okay? For women, on average, this number is smaller, 42%, okay? Now, of course, why we didn't mention white blood cells and platelets? That's because the volumes of those are so small compared with red blood cells that they are negligible when you consider the volumetric fractions. Okay, and so men has a higher hematocrit than women. Now, there was a time people were hypothesizing this may be one of the reasons why men tend to have, stroke tend to occur more often in men than women. Okay, so that's one of the parameters that we often use when you talk about blood. Okay, now. Another thing that we that are important to talk about in blood rheology is red blood cells. They have large deformability. Red blood cells, as you know, in their sort of native state, they have this, if you look at it from the side, we have this biconcave disc shape. So if you look at as a disc, then the radius is about 3.9 microns, and the thickness here, or half of it, is about 1.28 microns. Okay? Compared with, let me show you some pictures actually. These pictures are on canvas, so all the pictures are here. So red blood cells in a native state. And the next one, a red blood cell and two white blood cells. Okay? So you can see the difference. White blood cells, they're spherical, and red blood cells have this biconcave disc shape. Now the difference between these two is what? The red blood cells have a larger, actually much larger, surface volume ratio. You know the sphere has the smallest surface volume ratio, right? So as you can see, white blood cells are like that, spherical shape. And of course, any other shape has a larger surface volume ratio. And with this shape, you can see it's even much larger than other common shapes, okay? This allows the red blood cells to do what? To deform easily, okay? You can see if you have a spherical shape with fluid in it, it's going to be hard to deform, because to deform, you have to increase the surface area, okay? But this, the surface area, you don't have to change it. You can change the shape easily without increasing the surface area of the cell, okay? So it allows the cell to deform easily. Why is that? Well, it turns out red cell deformability is a very important factor for the blood viscosity, okay? So when you look at the blood viscosity, or when you shear it, you look at the stress. So the blood viscosity will depend on the hematocrit. That's the first parameter or factor we mentioned. Will depend on the deformability. And also shearing. So we kind of mentioned all these already, okay? So mentioned that when we talked about a few different kinds of non-Newtonian fluids, when you measure the shear stress of blood, when you change the shear rate, you will not get a linear relationship, okay? So that means you get a curve, okay? So viscosity will change when you change the shear rate, okay? When you change the deformability, the viscosity will change too, of course. So young people tend to, your cells tend to deform easily. So when you get older, the deformability of red blood cells will go down, okay? And as a result, the blood viscosity will go up too, okay? So again, the increased blood viscosity was hypothesized to be one of the factors for causing cardiovascular diseases and including stroke, okay? So hematocrit, that's very easy to understand, right? When you increase the number of red blood cells in blood, well, that will increase the viscosity, okay? It's like you're increasing the particles in a suspension, okay? So, so we'll talk more about this later. But I have more to show you why this is the case, okay? So over here, platelets, how they look like, deformability. So red blood cells, okay? You can see 3 different tubes, 10 micron, 6.6, 4.7, okay? These are the typical sizes of blood. Capillaries, okay? So the capillaries, their diameters tend to be in the strength from 5 to 10, maybe a little more microns, okay? So you can see how much the red cells can deform when they flow through these tubes, okay? All right? So any kind of shape. So they are capable of very large deformation to adapt to different flow environments. To do what? To reduce the resistance of the flow, okay? All right? It's like when you're moving, if you hold a large cardboard, right? Then your resistance is higher. If that cardboard can deform like this, then you know you experience less resistance, right? Okay, so deformability is one of the important factors for affecting the blood flow viscosity, okay? Not just in this kind of flow, okay? In the blood flow in large veins, arteries, and there the red cells will deform too, okay? To reduce the flow resistance. So of course, if you have large resistance to keep delivering all the nutrients to various parts of the body, because now the resistance is higher, you have to pump what? Harder, right? So that's why you have hypertension, okay? So all these pictures are on canvas, okay? Now this is the study where they showed the contributions from various factors to what? the blood viscosity, okay? So this is the relative viscosity, which is basically the ratio of whatever blood viscosity to the ratio, to the viscosity of water, okay? All right, so you can see these are plotted on the log scale, okay? 3 cases. Normal plasma, NP. So this is where the red blood cells in normal plasma. That's this curve here. So you can see when you increase the shear rate, this was done with cone plating, okay? So you can increase different constant shear rates so that the fluid is experiencing the same shear rates. You measure the viscosity, okay? You get the shear stress, you divide, you get the viscosity, okay? Okay. So here, as you can see, it's about 100. So since the water viscosity is what? Around 1 centipoise, okay? More or less. So this is like 100 centipoise, that large, blood viscosity, okay? So you increase the shear rate, the viscosity will be smaller and smaller. So at this point, we know at least blood is shear thinning. Okay, so I mentioned before that it's the high molecular weight polymers, the solution of those are light blood, shear thinning. Okay, so shear thinning. So you see, when you reach the shear rate about 100 per second, after that, maybe 200, okay, the viscosity, well, will tend to be the same. Okay, so after that point, about 200 per second, or 100, depending on how accurate you want it to be, the viscosity does not change anymore. Okay? Now, why is that? Okay? It's similar to the reason I described for the shear thinning behavior of high molecular weight polymer solutions. Okay? I'll come back here later, but blood, red blood cells, they can adhere to each other. Okay? We have proteins or molecules in blood, in plasma, that can connect or promote the adhesion of red blood cells together. Okay? At small shear rates, in other words, you take some blood, let it sit there, okay? And the red blood cells, they will form aggregates like this called rouleaus. Okay? All right? Just like those high molecular weight polymers. At a low shear rate, they can stick to each other and form aggregates. This is the reason why the viscosity is higher. Okay? Because of these interactions, just like molecular interactions. Okay? As you increase the shear rate, what's going to happen? You increase the shear rate, basically you're moving things faster. Basically you're increasing the, well, separation forces among these aggregates. So you're going to break these aggregates into smaller ones, and smaller ones, and smaller ones, until what? Everything's broken up. Every individual cell becomes an individual cell again. That's when you reach somewhere here. From that point on, the viscosity is not changing. Okay? And that's blood. Okay? All right? So, of course, you can see this decrease of viscosity. So part of it is due to that. Okay? It's due to the aggregates or aggregation of red blood cells. Okay? There are other reasons why the viscosity decreased this much. You can see this word aggregation here. So that means this difference here is due to what? Red blood cell aggregation. Okay? So that means the rest of it is not. Well, the rest of it is due to what? Well, part of it is deformation. Why? Because, see this is HA, hardened 11% albumin. So this is when you put red blood cells in albumin solution. So basically, we got rid of the molecules that will promote the adhesion of the red blood cells. Okay, so no aggregates. Okay, all right. So if there's no aggregation, and also red cells cannot deform, harden. You can fix the cells. Okay, using like formaldehyde. Okay, and then the cells cannot deform anymore. No deformation, no adhesion, no aggregation. So that means here the viscosity is purely due to the presence of these particles or cells. Okay, no deformation, no aggregation. You can see it's a suspension of particles, right? Viscosity doesn't change much. Okay, more or less a constant. It's higher than this because what? The cells are hardened. Okay, all right. That's why we call this due to what? Deformation. Okay, all right. This is due to what? Aggregation. Okay, all right. So 3 major factors. All right. So aggregation, deformation, and shearing. 3. Okay. Okay. All right. This one shows how the hematocrits affect the viscosity. Okay, so this viscosity here is basically centrifuges. Okay, here, right? And that's the hematocrit members. Okay, all right. So, so you can see higher it is, obviously we have a higher viscosity. Okay, all right. So that's that. Well, this one shows the difference between the red blood cells of a patient with sickle cell disease. Okay, this is one of the major type of sickle cell disease, hemoglobin SS type. Okay, if you look at the sickle cell, they're like this. Okay. So basically, sickle cells are very hard to deform. Okay, so their deformability is much lower than normal red blood cells. Okay, so the result, of course, their blood has higher viscosity. Okay, as you can see here, compared with normal blood. Okay, all right. So of course, yeah. We talked about different viscosities. Okay. So, what kind of equation can we use to describe this kind of non-Newtonian behavioral flow? Okay. So we'll talk about that on Thursday. Okay.